This is a little more nuts and bolts than what we've talked about. So the big vision stuff, this is getting down to some detail. In the abstract, I talked about looking at the state of Arizona. I'm going to focus on something a little more detailed than that, actually, in a similar application, looking at how to adapt systems over time and design water supply systems. And the key premise that I really want to get to is that when we typically look at engineering systems, we look at a whole spectrum of disturbances that we want to look at, that we want to be able to satisfy over time and be able to work through. And we really have this full range of chronic disturbances like climate change, population growth, things that evolve over time that are relatively slow that we have to adapt to. But at the same time, we have these acute things that we have to try to match up. And generally, and I don't think there's much out there trying to get both ends of the spectrum. And that's where we're really struggling, trying to be able to assess both the long term and the short term. So I'm going to really talk about the adaptive, looking at long term here, and then see how that really turns out to be a big problem for us. So considering just a water supply system that we wanted to design over time, we have a 50-year planning period. We're going to look at a relatively local scale for a region around 250 square miles in the city of Tucson. We'll be looking at our supplies, our demand is increasing over time, and the question becomes, how should we expand the system over time to be able to get this to operate properly and be able to meet demands? I drew this as a straight line here, and you can sort of see that fuzzy background, but I'll make it a little stronger here. As we're evolving over time, we don't know what's going to happen. We don't know if we're starting low and we end here or end down here or be even flatter than this. I've shown this broad range here, but what is the full range of potential possibilities that are going to happen, and how we could develop a system that we can modify over time without investing too much to get it to work and waste money either by over-designing or having to come back in quickly to make changes to the system. So I'll use something like the Bruneau definition of resilience. I'm plotting functionality over here, and functionality is defined here as the ability to supply divided by the ability by the demand of the system. So essentially, it is the red divided by the blue, or the light blue divided by the dark blue. And we could see then a couple of options. If we did immediate build out to build everything we needed to right off the bat, we would have lots of functionality and lots of capacity to meet our demands in the long term. But that's going to be expensive because we're investing everything up front, number one. Number two, we may not need that capacity over time. So the alternative is to go down here and build it in stages. So we could build that red, green, and blue lines over time. And we start with high functionality, but as over time that demand increases, and we start losing our functionality capacity and have to jump back up over time. The benefit there is that we have more adaptability in the system. We can make changes over time. And is it better though? Because what we end up with, and I've blown up this blue area here, I show it as a nice smooth line, but in reality, over time, we're going to have disturbances, these little disturbances over time, that power outages, failures of pipe systems or pump systems, increases demand, high demand days. So at some point, there's not a 1 there, but you can see functionality, and we have failures over time. So by living closer to the edge, we're more likely to have these short-term and be affected by acute events versus having just worry about the chronic ones. So the question is, what decisions do we make here over time to be able to be adaptable? And that's really what I'll be focusing on today. And then seeing that, how can we get to this point? So I described that first part as planning robustness, having a robust system that's adaptable over time, taking into account economies of scale for construction. Looking down at the acute events, blowing up that small piece at the bottom, now we have these short-term failures, and I describe that as design robustness, and getting a design that's going to operate under a whole range of different conditions. And the robustness part is remaining above functionality line. And I described resilience, unlike the NSF fellow yesterday, as just the part that we return back to recovery. So robustness is trying to stay away, and resilience is trying to recover. I'm going to jump through this because with 20 minutes, I'm going to run out of time. What I want to talk about here today is an application of scenario planning to be able to get to this point that we just talked about. And we can look at a couple different things here, including this idea of decentralization that came up in several of the talks, and how that affects resilience, as well as how it affects the ability to adapt over time. So in water supply systems, the traditional system is a centralized water treatment plant. We get water from one source. We send it through the blue pipes into the system throughout the city, and we return all our wastewater down here to a centralized wastewater plant. If we need to reuse that water again, if we don't have to send it to a river, and this is typically in Arizona, we take that water and distribute it back through the networks, and we have purple pipes that get the water back to the folks. The question becomes, is it cheaper and more efficient to decentralize systems and introduce satellite plants, these smaller plants in the system, and treat water at those locations that are closer to the users, reducing energy costs and collection costs, but having higher capital costs because we have more investments in those satellite plants. So we can look at that question with respect to the idea of being adaptable over time. So I'll talk about a straight application here. This is the city of Tucson, southern Arizona. For the longest time, we were getting our water from groundwater in the local region. We had to stop that because we're overpumping the aquifer. We're taking more out than was going in. It's causing land subsidence, among other things. We're now getting our water from the Central Arizona Project, around 335 miles or 500 kilometers. Mostly American, so I could say in English units, I think. So it's about 335 miles away, coming through Phoenix and down to us. We get our water from that source. We recharge that water and then extract the water back out. That's the whole story why that has to happen, but suffice to say that we do that. We send it through a water treatment plant and send the water throughout the region. We have two centralized treatment facilities that are located within 1 mile of each other. Really close. What's going to be happening though in the city is this area down here is largely undeveloped. Those of you who've been in Tucson, this is the airport down here. Raytheon Systems is down there. This is really largely undeveloped and will be developing over in the relatively short term. At least that's the expectation in the next 30 or 40 years. So that's this area here. It's around 250 square miles, a relatively large area, and with virtually no infrastructure in place. So it's really a greenfield that we get to start from scratch. The water supply is going to come in from this location. The wastewater plants are way up here, about 30 miles away. So what we're looking for is what infrastructure to be developed in this region to be able to supply in the long term. Should we include satellite plants? And how can we make the system adaptable? So because we don't know the rate of growth, and the expectation was that we're going to have lots of growth, and in the past 5 years, growth in Tucson has essentially stopped because of the economic downturn. We were hit really hard when the economy stopped, and the economy did virtually stop in Arizona. We're looking at how to design for the system. This is a blow up. You can sort of see this blue line out here, which matches up with the red one. The red dots are potential wastewater treatment plant locations. That's owned by the county, Pima County, which is the wastewater supplier in our region. So these are potential locations where we could locate satellite treatment plants if necessary. They have land available for us. For the water, in terms of water supply, this would be what our network would look like. Our elevation is increasing down to the southwest. So we have lots of pipes in here. These are, it's around 500 or 600 feet difference in elevation, which means we have to have lift stations to be able to pump the water up, and that's what these things are here, lift stations. The 1 to 6 are those wastewater plant or satellite plant potential locations that I mentioned a minute ago. So the decisions that the utilities want to look at, and there's actually 2 utilities here, which becomes an important point. First is the county, which treats and provides wastewater, or treats and makes it available. And the second is the water department. The water department is owned by the city and operated by the city. So we have, as you might expect, 2 conflicting and potentially conflicting organizations operating water and wastewater. So they have to get together and have some common ground to where they're going to work. What we're looking at here then is designing for both. Pipes and pumps for the water people, water reclamation plants, wells for pumping if we reclaim that water, and recharge and recovery facilities, because what we do with our water after we treat it is put it in ponds and allow that water to infiltrate to the ground. This is called indirect potable reuse. After treatment to a reasonably high level, infiltrating to the ground provides a barrier to remove bad stuff. Okay, so it removes microbial activity primarily, and then we can extract that after some period of time it's in the groundwater. So the approach that we took was a scenario planning approach. Typical design process, if you're an engineer, you sit down and your client tells you, this is where we're going to be in 50 years, get me there, tell me what the system should look like over 50 years. In Arizona and elsewhere, scenario planning is becoming a reasonable approach and a reasonably accepted approach for looking at things, and given the idea that we don't know exactly where we're going to be, and how do we really want to get to a point where we have a range of potential outcomes. And I just show from point A to point B, but actually there's a whole series of points in between as well. So scenario planning started with Shell Oil and worked through the Army. I won't go through that, so some of you know it. But the idea is to sit down, define a problem, determine what's going to affect the problem, determine the uncertainties, create some scenarios, describe a scenario. And as engineers, we want to really take that last step, which unfortunately I see a lot of scenario planning get to this point, describe scenarios, and then stop and saying, this is great. We know we know the potential outcomes, but there's no answer. And it leaves you sitting there saying, well, this is great stuff, but what's the answer? So we're really focusing on trying to find a path for the scenarios and then find out what actually we should do. So I'll walk through again. This is our frame the issue question. We sat down with the city and county, with wastewater and water folks in the county, and essentially spent about 6 hours defining the problem. And it seems pretty straightforward when we say we want to supply water to these folks, but it took 6 hours to define the region, set the parameters out, essentially set the scope, right? Because nobody wanted to be shortchanged. So framing the issue was really a hard problem. Identified driving forces. They sat down and identified everything that would affect the system, from perceptions about direct and indirect potable reuse, supply factors, demand factors, institution policies, and then rank those policies on a scale from increasing uncertainty and in importance, and wanted to look at the things that appeared here in this sector, which is high importance and high uncertainty, because those are the things you really have to consider when you're making planning decisions. And it really came down to three factors. What's the supply? Because as you may have read in the paper, Colorado river flows are being affected by a long-term drought. And as that long-term drought affects, Arizona is the first on the list to get hit. And the cities are one of the higher priorities for getting hit. So supply is certainly an issue. Demand, because we don't know what the population growth is going to be over time. And then this idea of public perception, which at the time we started this study was really important. Because the question was indirect potable reuse being acceptable and as an acceptable option. So we can then take our scenario matrix for the three different factors and develop scenarios depending on combinations of those factors. And this is a straight scenario planning process. So we ended up with 8 scenarios, but oops, I'll go here. It quickly became apparent to the city, and because they were doing some significant outreaches, that the idea of using indirect potable reuse was going to be acceptable by the community without doing high level of treatment as an outcome. So we actually were reduced from 8 scenarios down to 4 scenarios, and what I'll show you here. And the 4 scenarios are high supply, high demand, high supply, low demand, etc. For the different combinations. The way we wanted to get to solve the problem then, this is the key point, we have a set of 4 scenarios, potential scenarios, and what we should consider here, there's a time axis along the scale here, And what we just did was determine solutions for each of those scenarios independently and said, how do they affect and what will we do if each of those scenarios played out? In this case, element 1 was always put in first and element 2 sort of in the second period, 3, 4. And over time, we developed these systems with the different components. The key factor, though, is what do you do today? And then can you adapt based on that starting today and then move forward? So in this case, it was pretty apparent from time 0 to 1, everybody or all scenarios said introduce element 1. So this is a really easy problem for those folks if that was the case, because it was really just put in element 1 and you're satisfied. And then at time period 1, you come back and resolve this problem and then determine which path you're taking and what you should do at that point. So what we did was solve individual scenarios, then come back and saying, with the moving window, fix the things that had to happen in the here and now, and let each of the other scenarios vary in the future. So for periods 2 and onward, things changed, but in the first period, we required them to be the same. There's our problem. It's a relatively complicated problem in this case because we have a highly nonlinear system here. Describing water flow is a nonlinear system, so it becomes a difficult problem. We have lots of decisions, and we're solving this by a genetic algorithm because we have the combination of those two things. It takes us about a day to solve one scenario on an 8-processor parallelized out solution. So it's not an easy problem to solve for us, and you'll see why that impacts us on this acute disturbances in a little bit. So I'll just walk through quickly what happened. This is a low supply, high demand case. This is what we would do in period 1. The lines tell you the pipes. The darker the pipe is, the bigger the pipe. The bigger the pumps, or the larger the pump, it means it's a larger capacity. So what you can see happening is we develop a main pipeline here and then distribute off of that. The 6 MGD up here defines the size of the satellite wastewater plant that we use. So we gave the option to either use the satellite plants or send all that water back up to that centralized facility. In this case, the model says, or what we suggest is that we develop a satellite plant, showing that decentralized, our first conclusion, that decentralized treatment is useful and is economical in terms of sustainable and overall cost. Period 2, which is the second period, which is from we did this from 2010 to 2020. Period 1, next 10-year period, and then finally a third 20-year period after that for a 40-year life overall. In the second period, we added a few pipes, not very many, and additional capacity up in the upper corner here. The result was after period 2 in 2030, we had a 15 MGD plant here and significant pipes again. It looks pretty similar to what you saw a minute ago. Period 3, we increased capacity again up in the satellite plant. Add very few pipes, but we add some pump capacity as we go through. So we put a lot of pipes in the ground initially, and then just add pump capacity in wastewater plants over time under this scenario. So that's what our ending system looked like. And if we do that for each of the scenarios 1 to 4, and HH is high demand, high supply, low supply, high demand, and so on across. This is what we end up with. Capital cost over the 40-year life, $6.92 million. Operation and maintenance, nearly $1 billion. A total cost of $1.5 billion to supply this, to set up the system. That's for a high demand case. For low supply, high demand, it's similar values. When we have lower supply, we have significantly lower cost. So now we have 4 scenarios, and they all said to do something different. And in this case, we generally put the wastewater plant where we just showed, but most of the other pipes we have to put in the ground with different sizes. And now how do we get an overall solution to be able to get to this point? To get a solution that's adaptable over time and can work for the first period. The number in parens here is important to us because that's the capital cost expended in the first period. So you could see nearly 3.5 or 3.7 million, $100 million for the high demand case, and down in the order of $200 million for the low demand case. So now we said, all right, we have these 4 potential solutions. Let's cut this down and get one solution, fixing that all scenarios must have the same decisions in the first period, and then again, on the out periods, we can change over time. If we do that, this is what we end up with, and we minimize the overall average cost. Now the number in parens is all the same because we required every design to be the same in the first period, and the cost then for the 40-year life, starting with this in the first period, was pretty similar. So you'd expect the final solution to be pretty similar. So the difference in cost is around $17 million, or $17 million between the high demand and high supply by putting a lot of investment up front. Similarly, low supply, high demand, we have a little bit of increase in cost here, which we describe as regret cost because we don't have perfect information. That's the cost that we have to pay. The interesting one is when we get out here, even though we put in nearly $400 million, a similar design to what we did for the high supply, the overall cost only goes up around $50 million. If we're way off and the demand doesn't project as we have in the high demand case, we still only have to pay $50 million extra. So it's a really nice solution in that we can adapt to this solution over time. And what we've adapted is we've increased the overall capital cost, but we reduced the operation and maintenance because we put bigger pipes, so the supply cost, the energy cost for overcoming friction in the pipes goes down. So this was we were very happy. We had this. We went down to the city and county and said, this is it. Here's what we got. And here's what we got. And said, all right, 5 years, this is what you should do. Well, first thing they said is, we've had no growth in the past 5 years, so we don't need any of this infrastructure. So we're really low in our projections overall, and we didn't give you the right scenarios to define because we don't need anything in the ground, number one. The second is, the water people looked at this and said, what if this pipe fails right there? We have no way, or we have a little way, but these are really small pipes. Otherwise, this is something like a 36 or a 48-inch pipe. We have no redundancy in the system because you didn't explicitly include that in your process. So there's no way to account for acute failures. And they sent us away, essentially. Said, go back and do something because now you have to get it. The problem is when we try to include acute failures, instead of taking 1 day for each failure event that we try to include in a model, doubles the time, or we increase it by 1 day because the computation time is linear with the number of failures that we consider. So what we did do was, well, suppose we require the pump station to have similar capacities as we go across, and that did work, and to at least a reasonable degree because we distributed the flow, but it was a back-end way for doing things without really explicitly including those acute failures. We said, well, we're just going to assume that these pump stations have to be similar sized or they can't carry more than half the flow. It worked, at least from an engineering standpoint, but it really was not what we really wanted to get to. Okay. Just a quick note. The other thing that it did was rather than just including one satellite treatment plant, it put 2 satellite treatment plants in the system when we required it to distribute flow. So we can then see that having satellite treatment plants not only helps economics, but it also helps resilience and robustness of the system. So the question then becomes, can we get to the point, at least in systems like this and large systems, that we can include both the uncertain future conditions as well as accounting for these acute failures? 3-level model that we can look at. These are the conclusions essentially that I just said. And these are a whole bunch of people who worked on this project. I would ask you we're just about finished the proceedings, and I hope to bring some with me today. We hosted Resilient Cities through the National Academy with Iran. This is actually Tehran, if those of you know the tower in Tehran. In Irvine back in 2014. The proceedings are coming out, and hopefully you'll see them in National Academies of Press shortly, and hopefully if you get those emails about what's being published, you'll see some additional papers on resilient cities.
First of all, I would like to say thank you for giving us a chance to present our research report in this conference. My name is Dae-hyun Yoo. I recognize my co-author, Venu Gerikapati and Ram Pendiala. We are all from Georgia Tech in Atlanta, Georgia. Today, I will present some work on modeling the impacts of low emission zone strategies. One of the big issues in transportation is the emission that should be reduced. to make better air quality. There are several policy actions of interest to reduce greenhouse gas emission and fuel consumptions. For example, government offer tax discounts to all individuals as they purchase eco-clean vehicle, for example, electronic vehicle. This research focused on modeling low emission zones. Low emission zone policy would be compared with bow. Without arrows, a bow cannot hit target from a distance. It is important how to apply low emission zone policy to curtail gas emissions and reduce fuel consumption. This presentation will show the arrow what approaches may be best way to tackle the critical current issue in transportation. That is, low emission zone approaches should be able to shift people to transit or use cleaner vehicles. There are four potential approaches for modeling low emission zones, such as follows. First, incentive would be given to eco-travelers who use cleaner vehicles to low emission zones. Second is to offer all travelers enhanced transit service to low emission zones. Third is to charge monetary penalties to non-eco travelers who drive polluting vehicles to low emission zones. The last is time of day based incentive. That is, incentive would be differently given across time of day. For example, during peak hours, a higher incentive would be given to eco-travelers as they travel to low-emission zone. These four approaches can be combined to be implemented. Low-emission zones are geographically defined areas that seek to incentivize green transportation choice or restrict specific categories of high-polluting vehicles from entering the zone to improve the air quality within the geographic area. In this research, we consider for giving incentive to eco-vehicles as eco-travelers come in a low-emission zone instead of tolling polluting vehicles. In addition to incentive-based LEG policy, enhanced transit service to LEGs is also considered. Therefore, emission reduction would be expected due to two reasons. First, to increase the acquisition and use of eco-vehicles. Second, mode shift to transit because of better level of transit service. Modeling LEG scenarios will be implemented by using an activity-based model system. In order to model impacts of low emission zones, an integrated model system called SimTravel is used in this research. The integrated model system comprises three major model components, namely land use microsimulation, urban sim, activity-based travel behavior model, OpenAMOS, and dynamic traffic assignment model, DTLI. Social data data, land use characteristic, incentive level, and eco-vehicle penetration are provided into activity-based model before running microsimulation. The activity-based travel behavior model and the dynamic traffic assignment model are integrated in such a way that there is a continuous communication between two model system along the time axis. The time resolution for exchange of information between the activity-based model, OpenAMOS, and the dynamic traffic assignment model, DTLI, is set as 1 minute. Every minute, OpenAMOS sends two all trips that depart in the given minute to DTLI, and DTLI in turn sends all the trip arrival information that reaches their destination back to eponymous for determining subsequent activity travel choice of individuals. Every 15 minutes, detail light provides real-time traffic condition to the activity-based model. Test region is a 3-city sub-region located southeast of the Great Phoenix metropolitan area in Arizona. A synthetic population is generated whose attribute distribution matches those of the general population. The synthetic population is used as an input to the activity-based model, which generates activity travel pattern of individuals in a day. In this research, test was down on 50% of population for the 3-city region in Maricopa County. The 3-city subregion in Maricopa County is selected to test low emission zone model. This subregion consists of 175 traffic analysis zone. 2 areas in the subregion are selected as a low emission zone, here and here. The 2 areas composed of 12 TAGs. These 2 areas are designated with heavy retail development because this kind of areas have a high trip attraction and low air quality. In this low emission zone test, 2 modeling efforts are derived. First is incentive-based LEG policy, that is, monetary or non-monetary incentives are given to travelers to low emission zone by eco vehicles. Level of incentive and corresponding market penetration of eco vehicles is estimated based on existing research in the area. 3 levels of incentive were tested: 50 cents, $1, and $1.5 per every eco trip made to the low emission zone, with an annual cap for each of the incentive levels. The incentive is intended to encourage purchase and use of eco vehicles. Second is to offer enhanced transit service to low emission zones, namely increase transit frequency from LEGs. For example, transit service to low emission zone made twice as frequent as in baseline scenario, and discounts transit fare over 50% to low emission zone. In this model, it offers enhanced transit service to entire population to attract to use transit to LEG instead of polluting vehicles. This slide is to show all the scenario employed in microsimulation running using the integrated model system SimTravel. First scenario is a baseline scenario in which eco penetration is 2%. This percent of eco penetration was observed in 2009 National Household Travel Survey data, only Phoenix region data. In second and first scenario, 50 cent incentive to low emission zone are given with 3% eco penetration. In third and fourth scenario, $1.5 incentive to low emission zone with 5% eco penetration. No enhanced transit service is considered in second and third scenario. In the last 2 scenarios, transit enhancement is considered for microsimulation runs. This slide shows a result of individual activity travel choice behavior before applying incentive to low emission zone. It's a result of simulation, micro simulation. This individual, who is a female worker, is an eco traveler in this example. Her first activity is a personal business, like go to ATM machine, and then come back home. Then she leave to work and stay at work until 2 p.m. As she is coming back, she visits to a grocery market. In this example, all location choice for her is out of low emission zone. This slide presents how the individual location choice and her schedule are affected by incentive-based low emission zone policy. She first leave to work in the morning and stay at work until 2 p.m. As she is coming back to home, she would go to the grocery market and pursue a personal business located at low emission zone to receive incentive because she is using eco vehicle. The micro simulation based model system used in this research is able to capture impacts of incentive based low emission zone strategies on individual activity travel choice behavior in reasonable sense. And I will skip these two presentations. This slide presents the result of a vehicle mile travel BMT and CO2 emission across all scenarios from micro simulation run. In the first chart, an increase of VMT is found because eco-travelers would choose low emission zones as their destination, although travel distance is a little longer. The second chart shows a result of CO2 emission across all scenarios. CO2 emissions are reduced with increasing incentive because eco-penetration is also increased. With the enhanced transit service, we can expect more reduction of VMT as well as CO2 emissions. Number of transit trips to low emission zone is increased 30% in the two scenarios in which enhanced transit service are offered to all population. On the other hand, the number of non-eco auto trips decreased to below 70%. It means that transit enhancement to low emission zones leads mode shift for major market segment of non-eco travelers to public transit. The three maps present change of number of trips at the TAG's level between baseline and two scenarios that are no enhanced transit service. Dark blue in TAGs means less number of trips destined to the zone. Dark red in TAG means more number of trips come to the zone. In the schematic map, color on low emission zone changed to red with increasing incentive given to eco traveler across three scenarios. Here, dark blue, light blue, and change it to red, dark red. Namely, low emission zones are chosen by eco travelers as destination for pursuing non-mandatory activities more often with increasing incentive to low emission zones. There is another observation around the low emission zone. Also, the trip happened more often because this one is a kind of trip chaining. People stop low emission zone and stop near low emission zone too. So this model system also able to capture the trip chaining effect on activity travel behavior. The three maps present the change of number of transit trips at the TAG level between baseline and two scenarios that are assumed not only incentive but also enhanced transit service to low emission zone. Color on low emission zones are changed to dark red in two scenarios in which enhanced transit service are given to all travelers, namely travelers who use high polluting vehicles would choose low emission zones more often to pursue their activity in the place by a public transit. But using public transit is not easy to stop the other place. So there is not many trip chaining effect on these results. The chart presents a result of total energy consumption across all scenarios. Fuel consumptions are reduced with increasing LEG incentive for eco-travelers. With the enhanced transit service, we can expect more reduction of total energy consumption. These charts show percent reduction in energy and emission from baseline scenario for all the other scenarios. It informs us that we can expect at least 4% reduction in energy consumption and every different emission from policy that offers incentive for eco-travelers and enhanced transit service for all travelers to low emission zone. In conclusions, the integrated model system called SimTravel is applicable for conducting analysis of low emission zone under realistic assumptions. Model result shows that LEG incentive-based policies promise reductions in energy consumption and emission by leading to purchase eco-clean vehicles and motivate usage of the vehicles, usage of the clean vehicles. As expected, transit enhancement could amplify the reductions of energy consumption and emissions realized through LEG incentive and policy because it induced mode shift on the majority market segment of non-eco travelers. It was realized that an effective low emission zone policy is a combination of incentive to eco vehicles as well as enhanced transit service to attract non-eco travelers.
So we've had two interesting talks, both in the same geographic area in terms of the policies that they're trying to consider and problems that they're trying to solve. And let me open it up to the floor for questions.
My name is Lauren Cook. I'm from Carnegie Mellon University, and my question is for the first speaker. So I have two questions. The first one is you talked about how your O&M cost was lower actually when you increased the CapEx. I'm wondering if you could discuss a little more about that. And finally, I'm wondering if you ever found a solution for the city after they asked you to add in all the events.
The first question is, essentially capital cost is largely pipes. So larger pipes with the same flow results in less friction, and less friction losses means less energy consumption. So by oversizing the pipes, we reduce the energy demand to move the water through the system. So although it's not optimal for a single scenario, but when we start combining scenarios, then it comes out to be better. So it's really just an energy, the friction loss. The elevation still has to, we still have to overcome elevation, but the friction losses are reduced. Pumping, yes, pumping energy consumption. Yep, pumping cost and the energy associated with pumping. We are going back to this, the city revised all their scenario in addition to changing, saying we need to do something with to account for redundancy in the system. they also changed all their scenarios on us because essentially they looked back and said, we're not getting the growth we projected. So instead of being a curve that essentially went concave down, now they're projecting concave up. And so we're back in the drawing board right now, making a whole bunch of runs for them, trying to get this to go again. So in fact, I have an email in my box, where is the scenario planning process? And I have to answer. Thank you.
Other questions? I have one for Dr. Yu. So when you made the assumption or you parameterized the modeling to have a 5% or a 3% penetration, why so low?
It's the literature is not very many available, but one literature mentions $1,000 1 year receive it as an incentive is increase 1%. 1% to purchase eco clean vehicle. So we assume 50 cents and is calculate 1 year is almost close to $1,000. So we assume 1% increase.
Okay. Other questions? Well, with that, we'll adjourn to lunch. Thank you.